So the first is, if you look at any simulation program like what we have seen with MM1, right, there are sort of three things. If I run the experiment just once, right, let's say if I am asking you for the mean delay with some lambda mu values, right, so if you run it exactly once, then you are only getting the value of mean, right, for a particular seed value for a given random number seed, right, and depending on the value of your random number seed, you know that the random streams can be different, right. So just reporting value based on one exact random seed is not accurate in the case of a system such as this, where the randomness can have an impact on your system performance, right. Simple thing is, let's say you are trying to do topology generation, right, and you are trying to do some sort of protocol analysis, managed protocol analysis. So you randomly generate a first topology first with some, right, so the nodes are placed in random positions, then you give them random speeds and so on. And then if you are going to tell me that I have run the simulation, I have compared AODV and OLSR, and OLSR is having better delay than AODV by a margin of 10%, and therefore OLSR is indeed greater than AODV. So the first question that will be asked if you submit this is that, okay, that is for one particular random deployment of topology and for one particular, right, generation of packets. There are so many things that are random in the system, the way the nodes are placed, the mobility, therefore the way that the nodes move, and also the rate in which the packet generation, right, different packets come at different points in time. So there is a possibility that but you got lucky with this particular simulation, you run it again, you find that AODV is actually better than OLSR and so on. So you have to essentially run multiple replications of the same system, right. So that is the first thing. So if you simply run MM1 with just one value, that is one seed value, that is not adequate. You have to be able to, so you have to have a mechanism to change the seed, right, and in the case of this modified version of Axiom, at least we have like 16 random streams that you can choose from, but sometimes it is important to use the same seed, so you should know what the seed value is. If you, so how do we initialize a random number seed in Unix, for example? You can use time of the day, that is what we normally do, but they say that it is really not actually that good of a seed, but we normally use that, right. So if I use time of the day, right, and then you run the simulation once, simulation crashes, then you run the simulation again, oh god, simulation crashed, let me run it again, second time for some reason simulation does not crash, right. Why? Because the random seed was different, therefore the arrival pattern of packets was different to your queue. So maybe something that happened in your queue when the queue started overflowing, for example, right. In the first case it is possible that your queue started overflowing and you did not really capture that condition, right, somewhere you set some upper limit to your queue running out of memory and therefore the system crashed. Second case, just magically the way the packets arrived, there was no real overflow of the queue, therefore the queue was running perfectly, your code was working perfectly. So in that case you then you're running into trouble, right, because you didn't know what the first seed was. You know that sometimes it crashes, sometimes it doesn't, and you all know that when the TAS runs it, it doesn't run, and otherwise it runs perfectly in your room. So that is sometimes, right, the TA is probably evil, but not you guys. Who has this, knows that these things will definitely crash your program, and therefore they give those as input values. So that is, boundary conditions normally fail, but in this case there is not even a boundary condition, right? It is just the two different random values. So you know that, so one sense you want to be able to replicate the same set of events when you run it again. So you should be able to specify a given random seed. So normally simply set seed or seed to 0, and then you know that the same sequence of random numbers will be there, so the same arrival of packets will be there, right, so that you can check if you fix your random seed. That is for debugging purposes. For debugging purposes, fix your random seed, know what the random seed, so that the same stream of a packet is getting generated, and once you figure out it works okay, then of course you have to change the random seed. Then it crashes again, you know that okay, for this particular random seed it crashed, so you have to go and look into the system and find out, okay. So in this case, so once all that is done, then you want to do these replications with different random number seeds. There are also other things that look at the entropy of the system. You can look at your slash, what is the thing that you can use? I'm going to take a look at what other things can be used. In the Unix system itself, you can look at some of the current system state essentially, right, try to take that, capture that as a seed, so that there is absolute randomness when you are selecting a particular stream, so that two different streams have no similarity at all. Okay, so let us say that I have computed, right, I have run the simulation for different random seeds, and then I am measuring some entity. So let us look at one particular entity. So in the case of our MM1 system, right, we are measuring the So you measure the mean delay, right, mean packet delay. Which is say mu, right. So this is for every replication you are getting a set of samples, right. So you are, let us say you run it for n replications, so your sample space is mu1, mu2, mu3 and so on, right. So you have a set of n values that represent what could have been the essential, the actual sample, right, which of the actual mean of the system itself. So we will say that let x bar, right, be the mean of this, right, and s be the so the simplest thing is to compute the mean of these means, right. I have done x number of replications and then I compute the mean of these means and I say that this is the mean of in terms of packet delay, right. But you can go one step further and actually compute the confidence interval. So the term confidence interval is known or is it new? Some of you have heard it, some of you have not. Some shakes and some no shakes. Okay, fine. So how do you compute the confidence interval then? How do you compute it? What is the definition for the confidence interval?
The interval you are computing, the probability of which it lies within that particular confidence interval.
You integrate the PDF. Integrate the PDF between 1 minus the integral.
Okay.
Depend on the
between these two. So you are given, so confidence interval basically is essentially two values, right? Two ends of the interval C1 and C2, and the probability, and usually there is also another parameter which we will call as alpha, okay, and alpha will be usually less than, right, alpha which is between 0 and 1, right. So the probability that the actual mean, right, this is not the sample mean, the actual population mean lies between these two intervals, these two values C1 and C2 is equal to 1 minus alpha. So if I tell you what the alpha is, usually we do it the other way, I tell you what the alpha is, then based on the mean of these means, you can actually tell that this is the probability that the mean for the system will lie between these two values with some with this 1 minus mu with the specification that we are actually providing, okay. So again there are some terms here, so this alpha is called the significance level, then your 1 minus alpha, so we normally put that in a percentage, it's called the confidence. So when I tell that the mean of the system, right, or the average delay of the system is given this confidence interval, we will say that it lies between 10 and 20 with 95% confidence, or 95% confidence interval is basically these two values 10 and 25, okay. So there is some way to essentially again compute this, modeling this as either a t distribution or a normal distribution. So again, so the confidence right, given your values of given that x bar and s is given by I will just make it x. there are a few terms here which I won't attempt to explain right now because I need to go through that once more. So for now we will just take the formula as such and we will come back with the actual figure of how this maps to the unit normal variate and so on. So normally if you have more than 30 samples, right, this is if your n is greater than 30, we go to the unit normal variate, and then there is a table usually that tells you, right, if you remember old fashioned clocks tables and so on, that tells you for the given value of alpha what is the corresponding value for this z, okay. And let us see if there is an example we can look at. Yeah, okay. So if you end up this book, you will find on the web too, you will find these values for the unit normal variate, right. We just take those values and plug it in. Most of the time it is readily available, and if it is less than 30, then we have to go to a different distribution called the t distribution, not the student tree distribution, right. So if it is this is, we would use the normal table, and if it is, if n is less than 30, then we normally use the student t distribution. Okay. So why this is important, we will just take a moment and see. Okay. So in this previous example that we had, we did not say any examples so far. Okay. Let us look at one numerical example, right. So let your x bar equals 3.9, the standard deviation be say 0.95, and n equals 32. Okay. So you have run 32 replications and computed the mean value of across all the mean, right, packet delays for the system. It could be any many metric. You are looking at one metric that you are measuring, and then this is the mean across all those metrics, right, whatever that is. So in this case, okay, now this confidence interval we normally specify in terms of 90%, 95%, 99% and so on, right. So the typical confidence interval specifications okay. So as the higher your confidence interval requirement or this confidence interval level, right, confidence level, then your window will, the interval will be larger, because you want to make sure that, right, 99% of all the or with probability 0.99, right, your system is going to have yeah, your interval represent the fact or the probability that 99% of the time your values will be, your mean value will be in this given range. That is what your CA represents. So the corresponding value for alpha is 0.1, is 1 minus alpha, right. So you start with the confidence level, then we compute the alpha, then we go and look up this table, right. So let us say for the, I want to compute the 95% confidence interval for this particular system. So I need to compute z of or z of 0.1 minus alpha by 2, so that is 1 minus 0.025. Which turns out to be, so many times you simply just if you really want to do it in the head, just say it is roughly proportional to equal to 2, right. So then your confidence interval is basically 3.9 minus So even though the single value computed is 3.9, essentially your window for 95% interval is 3.57 to 4.23. So this means that 95% of the time the mean value will be within this particular range. Okay, this is your first analysis. If you want to have 90% confidence interval, then you have z1 minus 0.1 by 2, that is 1.64. And therefore the confidence interval actually will work out to be right. So 90% interval will be narrower because you are giving more leeway in terms of the expectation of what your what the mean value should be. This is from the table, yes. So it's mu is not just a single, right? It will lie in this range with this probability. So mu is the mean delay, yeah. Because you never really know what the real delay is. You're only looking at a right. This is we have a set of samples, right? You could run this for a million times, right? The larger your n, then your smaller the range is going to be. If you run it for 10 million times, for example, and you compute the mu's each time, the average delay mu1, mu2, and so on, you will find that the actual variation you will have if you look at the average of that will probably be more representative, right? And therefore when you have a larger sample size and less standard deviation, right, if all the mu values the mean values computed at the end of each experiment are fairly close to each other, your deviation will be less, right, variance will be less and ST will also be less, in which case again your interval is going to be fairly small.
Should terminate with 95%.
Yes, okay, yeah. So what? Oh, so now we will, yeah, we'll get that is the batch means part, which I haven't yet done, right? That is there I'm not doing replications. I'm just doing means batches within the simulation and I'm computing the batch means. Okay.
In your MM1Q, sir, you have that replicate flag.
Yes.
What does it mean that E of n stops changing when you terminate the program?
Okay. Yeah. Use the replicate flag. No, I mean, if I use the replicate flag, then it will try to auto terminate and use this auto terminate function. Otherwise, it will simply run for the duration that is specified. Yeah, so I will just come to that termination part in just a second. Here is a set of samples, and here is the interval, right? The 90% confidence interval based on the set of samples, mu and sigma values. Okay. So if you go to 99%. Then your the z value for this corresponds to will be larger. So in general, as your confidence interval or level increases, the corresponding z value will also increase, in which case your window will correspondingly get larger, right? So and if your S is very small, which means that very little deviation, right, between the different runs, between the different replications, and therefore you know that like the range in which your actual value will fall is going to be within this very small range. So the square root of n is there, right, in the formula. Square root of n is needed or is not needed, divided by square root of n, because later on in our same Rajan book he dropped the square root of n. So he has two different versions for the same formula, but from what I know the square root of n is included, should be there, right. So there are still some errors that even after multiple editions they are not fixed. This is the most recent edition. Okay, so what is the corresponding interval here? So in other words, when you report, right, values in thesis or papers, whatever it is, right, you just can't, you just say that this is my one single mean value, right, and then compare. We'll look at comparing two different systems later on. So just simply comparing two means is not adequate, right. Even though I'm running replications, you also have to look at the confidence interval for both those two different systems, A, system B, and you say system A's mean is better. I've run this for 1000 times, and right, based on the means alone, you simply cannot compare. You should also compare based on the confidence intervals, only then you can conclusively say that A is better than B. So we will come to that later on. Okay. So in so sometimes have you seen GNU plots or plots where they actually, right, plot? Yes.
So we are running two types of systems, and if we are taking the confidence interval for both of them at 99%, how do we say that this is better? Is it the higher the value it is better?
No, the interval should not overlap. The simplest thing is the interval should not overlap. If I have two systems that I am comparing, right. So in this case, for let us say I am comparing 4 systems, right. This axis is simply the system type and this is your metric, right. So you would have seen this, you can do this in GNU plot very easily, right. If you just have one more value, so if x, y, and then the third thing is your confidence interval, so it will automatically compute the plus or minus for the confidence interval, right. So this is the mean. I have not drawn it perfectly, but the mean is in the middle, exact middle of these bars, right. So now if you look at it, right, visually speaking, you find that there is overlap, right. The upper end of this system overlaps with the lower end of the system, so therefore there is a non-zero probability that the system might actually be operating, right, by the end of the delay for the system or metric for the system might actually be here, right, and the delay for the system is actually here, in which case they are not statistically speaking, they are not significantly different, they are the same, there is no significant difference. If I really want to say that system A is better than system B, then I want something like this. Let us say this is throughput, right, so you want higher throughput should be better. If this is A and this is B, so I implement system A, implement system B, and then there is a clear visual separation, right, between these two intervals, then you can say that one is better than the other, right, and especially larger the confidence level. If it is 90% confidence level, then you might say okay, right, maybe there is a small chance that if I expand the confidence interval, then it is possible there will be some overlap. At 90% there is no overlap, but 99% that might be overlap in the system, right. So to really say that one is better than the other, right, we should have this. And there are other smaller conditions too, but this is the simplest one that one can visualize. If we can get a graph like this that compares two systems, that too after a large number of replications, right, so more the replications, better the confidence in your system. You are running say sorting algorithms A and B, and then you are running it right with several different data sets, a million different data sets, then there is more confidence than just running with 10 different data sets, because as you increase your data set number of data sets, your n value goes up and therefore your confidence interval also starts shrinking, right, so therefore your range will get smaller. So that is the first thing that one has to realize, that when you report results, right, it has to be reported with replications and the corresponding confidence interval for a given metric. So that is the first point that I wanted to state today. Questions? In your next assignment there is no comparison of systems, third assignment we will do comparison of systems.
Here the confidence intervals are same for all the systems?
No, these are differences. A, B, C, D have different confidence intervals, right. Let us say this is delay, right, so this is say 10 and this is say around say 4 or something like that. So this guy's interval is between 4 and say I don't know, this is 5, right, and this is say between 5.1 to I don't know 8.9 and things like that. So these are the actual confidence intervals. So what I am plotting here is the actual intervals, right, so the corresponding to the y-axis values.
So that percentile, what I was asking is the
Yeah, this is, let us say this is the 95th percentile. Let us say I am plotting the 95% confidence interval. I am running these 4 systems, right, and let us say this is sorting A, B, C, D. I am computing the time taken to sort, and I am just time taken to sort is the metric I do for each replication. I run this over several million data sets, right, then I compute the mean and compute the CI based on the standard deviation for that particular data set for a particular algorithm A, and that is what I am plotting here in this manner.
So what I was actually wanting to know is that system A should be all A, B, C, all those should be on 95%.
Yes, no.
One should be only 80%, another is 90%.
Sorry, yes, that's correct. Yeah, that was simple. Yeah, it's a long answer to the short question. They should be all on the same confidence, otherwise it is meaningless. And let's say this is 99%. Okay. So the trick then is, off the record, when you write your thesis or report, you find that 99% there is overlap, then go for 90. Then where there is no overlap, so therefore you can say your system is better than the other one, right? So it depends on when you want to finish your thesis and leave. Okay, so that's the first aspect of what I wanted to talk. It is a mean. It is a sample. It is a sample standard deviation. CI, right? Based on these samples. So it is mean of these samples and S of these samples. This is not the sample. It's not the population standard deviation, because this is all that you know, right? You compute the standard deviation, and this is what you can compute.
what estimator is it exactly? Could you just write down S in terms of sigma?
What we estimate as the population standard deviation from the sample standard deviation
Okay, no,
as
this
that
is,
n minus 1 by
sorry,
n
sorry.
factor.
This is your standard deviation as computed from the samples, right? So if you, I guess your variance, right? So S is your square root of 1 over n minus 1. This is what I am looking for. So yeah, this is just based on the sample statistics. I don't think we are going to the, we are estimating the, so you are talking about estimating the sample, the population standard deviation from the sample list. Next, so there are two aspects of running simulations, right? So if you look at say measuring, let us say we are measuring the average delay per customer per packet in the system, right? And let us say this is J, right, is your observation count, or basically jth customer who is departing the system, right? And you are now plotting this with respect to increasing J, right? For the first customer, the mean delay is whatever value that you saw, right? So this is simply one, this is the mean packet delay. So you probably know this already, right? So first will be simply whatever value that you get first, right? And then this value will be just going up and down, right? The mean value will be unstable for a while, or not unstable, it will be, it's at the transient state of the system where the values will kind of jump wildly up and down, right? And as your J value increases, then your, and if your system is getting stable, right, then slowly your system will finally converge at some point too, right? There will still be some variation, but over time your steady state will be reached, and this is essentially what you will call as a steady state mean delay, mean packet delay for this particular system, right? So your system will always, especially if you are looking at a network of queues, the queues are all empty when you start with, and then as and when packets arrive into the system, then the queues start getting populated, and then slowly the system's queues start getting built up, and once the queues are built up to a certain point, then addition of new customers does not really change the behavior of the system, right? So your system is essentially entering steady state. So your behavior of the system is essentially, this is your transient state or initial state, right, and then this is finally where you enter steady state. Okay. So when you compute the mean packet delay, so the final value that you compute will also include some of these initial delays, right, where the system has been sort of, the initial observations are also included in that. So there are two things that you want to do. One is, if your goal is to only look at steady state values, you do not want the values to be corrupted by the initial transient state of the system. So you want to be able to figure out, right, you want to exclude these values. So you do not want those observations at all, because you know that it does not matter, because the first guy could have delay of 0.01 and the system delay is actually 10. So 0.01 just happened that this particular customer had just 0.01 seconds of service time, the real service delay is much higher, the average service delay is much higher, right. So you want to exclude the system state when it is when it is in the transient state, right. So that is the first thing. So this is so called initial data deletion. So that is what you would normally want to do to get rid of the stand. If you are only interested in the steady, sometimes people only want to study the transient state, that is a different story, right. So but that's then in this for steady state analysis, and then when you go to steady state also, right, the classic question is, when do I stop my simulation, right. So simulation termination condition, right. So because if you keep recording the average values with every observation, right, it might be varying between some values, it is not going to be a constant value if it is totally random, right. So it will be varying between a few set of values, it will kind of jump up and down, right. So you would see that, and then okay, when do I say that enough is enough and I will stop my simulation. So of course the simplest thing is for initial deletion is just ignore first 500 units or 500 customers, because I am running this for 1,000,000 customers, so I do not care, first 500 customers will not really make a difference to my system performance. And likewise termination condition, simplest thing is run it long enough, right. Usually it is dependent upon when you want to finish your project and leave. So if each simulation is going to take 10 hours, if you really want proper termination, right, that driver auto terminate, if you let it run, it's going to run forever unless you give that other parameter saying heck with it, just stop at this point and compute, right. So you want to be able to scientifically say that system has achieved steady state, there is no point in running any more simulations, right. So usually just based on some sort of variance computation or change in values computation, right. So these are the two things that we will talk about, how to do this data deletion, initial data deletion as well as simulation termination without arbitrarily choosing some values, right. Easiest thing is to just choose arbitrarily and move ahead, but if we can possibly do something better than that, then what are those techniques? So techniques to remove transient data. So the first is just run the simulation for a very long time. Easy. For the MM1 system actually you can do that because it is a simple system, right, not much of computation is involved, not much of background processing is there, right, in terms of state changes and so on. And of course the question is how long to run. So this will satisfy both your problems, transient state as well as steady state, how long to run, just run it for a day and then see what happens. But there are some systems which are much more complex, right. We have our students running simulations with OpNet for ad hoc network simulations and so on for 5 minutes of real time, right, it runs for a day if I really want to get high accuracy. So 24 hours they would say per run, and then I say run each thing for 10 times or 20 times for replication sake, then they say 20 days for one value, right, and then this is only for one particular combination of metrics. Then I say okay, change the number of users, change the combination of traffic that is getting generated, right. So then nobody ever takes up the project, they say no, can I do something simpler where there is no discrete event simulation. So discrete event simulation systems, and if you are trying to do something like a even large scale system like molecular dynamics and things like that, right. So there too it will take a very long time for to do all the computations that is involved. So therefore running simulations for a very long time is easy, but it is sometimes not practical. Okay, so that certainly is not going to work. And the second is to look at initializing the system with some initial state, assuming that you know what will be, let us say that I am looking at network of queues, right. You would normally start a simulation by saying there is no customer in the system, customers will slowly start appearing one by one as we saw in our MM1, and then I can look at therefore I can just start from state right ground zero. The other way is to say that I can just fill some of these queues with one or two customers, right, just to essentially fast forward your system to some future point in time where there are customers sitting in each of those queues with their corresponding service times and things like that. So you basically start your system with some part of your initializing basically takes care of some initial behavior of the system itself, right. You are just moving the system forward in time to some relatively intermediate futuristic position from which you can then start computing, right. The only thing is how do you figure out those initial values, that is the hard part, right. So if you know, sometimes it is possible if you have say trace files for example where you can use that to populate your system and then say this is the initial buffer occupancy and queue occupancy and so on, right. So this needs knowledge of how to initialize the queues and so on, right. So that is another way. So you are basically starting from a semi steady state, right. So semi steady state is when you have a little bit of alcohol, right, and steady state is when you have none. Okay.
When you say a semi-steady state, you also need to figure out what is the semi-steady state.
Yeah, you don't know. Yeah, so you just that is why you call consultants. Okay. And you pay them lots of money, tell you what the steady state, where you should start from, right, then they will tell you. Then there is this notion of truncation, right, this will be delete the just the initial set of observations. That is again nothing, just simply, right, one is simply run long run, other is to randomly say first 50 observation, 500 observations, we talked about that. You can also delete that, but we can be a little bit more I guess mathematical about that by saying that, right. So you have, let us say, a set of samples, that much I can remember. Okay. So this is the just some values that you are measuring from the system, right, whatever this is, delay, some metric, okay, waiting time. So the basic logic is, right, ignore the first L observations, L is some value, right, of the, let us say you collected n samples total, right, n samples, and compute the min and max of the remaining n minus, right, observations. So L is some index among from 1 to n. For a given L, I am ignoring the first L and looking at the min and max of the remaining observations. And then if XL, right, is not equal to the min or XL plus 1, and stop. And then delete. I am sorry, it is neither the min or it should be in the range.
It should be in the range means not, can't just say not equal to, check for the range.
Okay, it should be
within the range.
Okay, yeah, it should not be the min or it should not be one of the two extremes, that is all.
That's
But it won't, because min and max, because L plus XL plus 1 is in your min and max computation, right. Yeah, it should not be one of the two extremes, that is all, because XL plus 1 to Xn is what you are computing the min and max over, and the XL plus 1 should not be either the smallest or the largest value. I know this is not perfect, yeah, this is a very crude approximation, right. It could be that the min is 10.1 and this value is 10.2, right, and you end up saying, oh, it is neither the min nor the maximum, right? So yeah, so this is a very crude way of doing it, but if you want to look at, so we basically in this case, right, so let us see in this particular example what happens when L equals 2, right, or L equals 1, I look at 2 to whatever all the remaining samples, minimum value is 2, therefore I will ignore them, right. So I keep doing this until I finally come to 10, right. When I look at if L equals 9, right, then 10 onwards the set of values is 9, 10 and 11, therefore the min is 9, the max is 11, the next value happens to be 10, which is neither the min nor the max, therefore I will stop. That is noticeably it is not the best method, because you are only talking about the two extreme values, right.